Hey there, Chem Scholars. I'm going to assume you've been around the kitchen before and ask you a couple general questions. So, you're cooking, you take a pan out of the oven, okay? Let's assume it's a metal pan made of aluminum, okay? Take it out, put it on the stove there, pull the food out. By accident, you brush up against it. Wait, it's not that hot now, okay? But on the other hand, you also took out a glass pan and take the food out and you bump up against that and whoa, I just got burned. Okay. Aluminum is a metal. We know metals are conductors, right? Okay. Well, they're conductors because they don't hold heat well. Okay. They have what we refer to as a low specific heat capacity. Specific to the substance, capacity, ability to hold. Okay. So heat capacity, we're talking about the ability of a substance to hold heat. Okay. Metals are conductors. They have low heat capacities. Glass is more of an insulator, so it's designed to have a higher heat capacity. Okay. It is supposed to hold heat well. The difference in cooking between those is important. Okay. Glass pans are usually used when you want to keep something warm on the table. Okay. You serve the food right in the glass pan because it's going to help hold the heat in. Whereas if it's something you're cooking in a metal pan, you're going to take that out because the metal's going to cool off, which would just cool the food more. Now, why then use a metal pan? Because it does heat up faster and cool down faster. So in a cooking sense, a metal pan is going to conduct a lot quicker, so it's going to speed up the cooking time, but be aware it could also lead to burning issues. But I'll leave that to culinary arts. I'm going to talk about specific heat capacity. Okay? All right, so the technical definition is the specific heat capacity is the amount of heat needed to change the temperature of 1 gram of a specific substance by 1 degree Celsius. Okay? So, for example, if we talk about water, it takes 4.18 joules to raise 1 gram of water by 1 degree. Now, a gram of water is a tiny amount, small drop. 1 degree is a small amount. It takes 4.18 joules. Okay? Joules are, we talked about this idea. They're kind of small units. You'll see some big numbers. Don't worry about that. So we say that the specific heat capacity of water is 4.18 joules per gram per Celsius degree. Now I'm going to pause for a moment there, and somebody's going to be wondering, why did I put the degree symbol after the C instead of before? It's a stupid little thing. I'm not really worried about it if you do it. When we talk about a change in temperature, technically the degree symbol comes afterwards. When you're talking about an actual temperature, the degree symbol comes before. I didn't make up the Celsius system, okay, so don't blame me. You'll see me do that, but I'm not worried about you doing it. It's just part of my training. I don't know how many people worry about it anymore, but it's just kind of ingrained in me. Anyway, okay, so you'll see it that way. So the symbol for specific heat capacity is the lowercase letter C. Some people will write it with a C with a subscript of a P because it's supposed to represent something at constant pressure. We're not talking about pressure yet, so I'm not going to worry about that part. We're just going to use the letter C when we talk about specific heat capacity. Okay, so let's compare water to some other substances. Okay, so first of all, water to ice. Wait, they're both H2O. Shouldn't they be the same thing? No. When we talk about specific, it's specific not only to the chemical, but also the phase of matter, the state of matter. So ice and steam actually are kind of close together, although we're going to differentiate that eventually. But you notice that water is very different, okay? And the properties of water we'll get into along the way in this course. But that's part of what makes water so unique. Now, by comparison, going down the rest of the list here, now we get into the metals. And you see that the metals have much lower values. Let's compare something like lead to water. Okay, we think of 4.184 as not being a big number, but compared to 0.16, it's really kind of a big number then. Okay, I mean, you're talking about something that is more than 10 times, okay, more than 20 times, almost 30 times bigger. Okay, so water's value of 4.184 is relatively high. Water is pretty good at holding heat. Okay, metals, not so good. All right, so we want to get into the mathematics of heat capacity, okay? And so we're going to see our first equation here. Q equals M times C times delta T. Okay, the triangle is called delta. In math, you learned about delta. It means changes. So delta T for us means change in temperature. M stands for mass, C stands for specific heat capacity, and Q is the symbol that's used for heat. Yes, I know that doesn't make sense. Why isn't it just H? Because H is used for something else. They call it a quantity of heat, so they use the letter Q. Okay, so I have the symbols and units set up here. So heat would be measured in joules, mass should be measured in grams, change in temperature should be measured in Celsius degrees, but if you say degrees Celsius, again, that's fine. Okay, and specific heat capacity is measured in joules per gram Celsius degree. Okay, and again, delta means change, so we're doing final minus initial. So if we take the final temperature, subtract the initial, that's telling us a change. Changes can be positive, changes can be negative, okay? So it doesn't always have to be a positive number. Right now, most of what we're going to talk about will be positive, though, okay? Let's talk about some situation, problem solving, and how to go about some of this stuff, okay? So example 1, how much heat is required to raise the temperature of 34 grams of tin from 22 degrees Celsius to 34 degrees Celsius, okay? One of the things I expect you to do when we are problem solving with equations and whatnot is to write out your givens and your unknown, okay? So I tend to tell my students to use the guess method, okay? G stands for givens, U stands for unknown, E stands for equation, the first S stands for substitute, and the last S stands for solve. Okay, so that's kind of the kind of work we want to see. So you'll notice that I wrote out my givens, wrote out my unknown, I have my equations. Then after I write the equation, I substitute in the numbers, and then I do the calculation or solve for it, okay? So let's go through the idea here. So we know the mass is 34 grams. We know the specific heat of iron is 0.314, okay? That was in the table that we saw on this slide here. It's not that I'm pulling it out of thin air, okay? And we were told that the initial temperature was 22 degrees, and the final is 34. Now I know mentally you could just look at that and say 12 degrees, and that's fine. I don't have a problem with it. I'm just showing you the thoroughness, so that's where the 12 degrees is coming from, 34 minus 22. Then I take my heat equation, because we're trying to solve for Q, right, our heat. I take the mass, 34, multiply by the specific heat, 0.213, multiply by the change in temperature, 12 degrees, okay? Now, as far as units, you'll see there's a gram here, there's a gram here, they're going to cancel out. There's degrees here and degrees here, they're going to cancel out. The only thing that's going to be left is joules. Well, that's what heat should be measured in, okay? Many of you won't include the units in your work. I don't take off there, but if your answer doesn't have units, I'm definitely taking off. When you do the math, you come up with something like 86.904. But let's review that idea of sig figs real quick, okay? I look back at our givens here. This was 2 digits. This was 3 digits. This was 3 digits. You go by the smaller number when you're doing multiplication or division. So the fact that there's 2 digits means my answer should only be 2 digits. So 86.904 is closer to 87. So we round it off, and our answer is 87 joules. Bam. Okay? All right. So now let's look at it in a different order. So now we're going to say that we have 317 joules of heat needed to raise the temperature of some water from 10 degrees Celsius to 25 degrees Celsius. And we want to solve for the mass. So I know Q is 317. I know we're looking for mass. The specific heat, again, for water is on the other slide. I've mentioned a couple times, 4.18. Okay. And our change in temperature, we're going from 10 to 25 is 15 degrees. I wrote it out, but if you just said delta T is 15, I would be fine with that. Okay, I write out my equation, Q equals M times C times delta T, but keep in mind, we're really solving for M. So what I did is I did the math and actually divided both sides by C and delta T. So I said that M equals Q divided by C times delta T. Okay, so M equals 317 joules divided by 4.18 times 15. Okay, so I get 5.05582 grams. Okay, I know the mass is grams. And again, I could see that joules would cancel out with joules. Celsius would cancel out with Celsius. The only thing left would be grams. That's got to be my unit. Going back to my givens, this had 3 digits, this had 3 digits, this had 3 digits, so my answer should have 3 digits. So I'm going to round off at the third number, 1, 2, 3. So it's 5.06 grams, final answer. Okay? All right, let's flip it around one more time here. So in the third example, I tell you that there's 518 joules of heat being added to 112 grams of lead, initially at 15 degrees Celsius. What is the final temperature of the lead? Ooh, this one's going to be a little different, right? Because we can't find delta T unless we know the initial and the final, right? Well, we can go about it in a different order. So we know Q is 518. We know the mass is 112. We know because we're told it's lead, we go back to that other table, and we see that the specific heat of lead is 0.160 joules per gram Celsius degree. We were told the initial is 15, and we're looking for the final temperature. Okay? So, see, I didn't put T final as T final. I'll just put an F equals question mark. Okay, so there's my unknown. All right. So now I'm actually going to start with Q equals MC delta T and solve it for delta T. Delta T would equal Q divided by M times C. Okay. Now I also know that delta T is T final minus T initial, so I could take this and substitute it into here. So I have T final minus T initial equals Q divided by M times C. Now if I really just want to be thorough and solve for T final, I'm going to add T initial to the other side. So T final equals Q divided by M times C plus T initial. Now I'm going to substitute in and solve. So I'm going to have Q 518 divided by M 112 grams times C 0.16. Do that out, and then I'm going to add in the 15 degrees Celsius so that my final temperature is 43.9 degrees Celsius. From a math point of view, there are several ways you could have done this without doing all the rewriting of equations. But that is a skill that will be tested along the way. So just try it when you can. Okay, you got to work on that idea. All right, one more manipulation. Sure, let's do it. Okay, we have a 125 gram ball of an unknown metal given 672 joules of heat to bring the temperature from 20 to 32 degrees Celsius. Determine the specific heat capacity of the metal, and then use the table on slide 78 to identify the metal. So we know mass, we know the heat, we know the initial, we know the final. We're looking for specific heat. My equation for change in temperature tells me that the change in temperature is 12 degrees, which could have figured that out just by looking. But yeah, Q equals M times C times delta T. So C would equal Q divided by M times delta T. So I'm going to take the Q, the 672 joules, divide by the mass, 125, and multiply the mass by 12. Sorry about that. And so when I do that, I get a specific heat of 0.448. And now I go back to that table, 0.448. What do you know? Our unknown must be chromium. Okay, so that's all there is to this. Okay, you're going to give it a try. And by all means, ask us questions. All right. Ciao for now.